So I'd like to first take this opportunity to thank the organizers of Parity Violation from Home 2024 for inviting me to give this talk on the recently derived cosmological CPT theorem in collaboration with Harry and Aaron, as well as my no-go theorem for cosmological parity violation, which should appear imminently on arXiv, hopefully by the time that the conference starts. And I will also be discussing some uh, some results which will be relevant to another follow-up paper where I check some of the constraints that are derived in this talk and the no-go theorem and this cosmological CPT theorem paper uh, for the cases of various loop and tree level diagrams in cosmology. So I would like to dedicate this talk to, in light of the 35th anniversary for Tamil Remembrance Day, to Lieutenant Colonel Sandosham Master and Talavir Prabharan. So I would also like to thank the Institute of Physics for funding me through the Bell Burnell Graduate Scholarship, as well as the University of Cambridge. Okay, so to start off with, in this talk, we're going to be considering scale-invariant boost breaking interactions on a fixed d equals d plus 1, big D equals little d plus 1 dimensional de Sitter spacetime. And specifically, we're going to be working in what's known as the Poincare patch, which is the expanding or inflationary patch of de Sitter. And this is described by the line element written here, which is actually conformally flat. And the conformal time eta runs from minus infinity to zero at what's known as the inflationary boundary, which then acts as our reheating surface in inflation. And what I'm particularly going to be talking about is how some of the constraints Harry discussed in his talk will manifest themselves at the boundary. So to start off with, I'll be summarizing the cosmological CPT theorem, and I will be just revisiting some of the constraints that Harry discussed in his talk, but I will be doing it in a self-contained way. However, if you are interested in this line of work, I really recommend that you watch Harry's talk as it will give you much more detailed understanding of how to derive these constraints. Then I will discuss how we can actually look at cosmology from a purely boundary perspective and where there's no time dependence, no dependence on eta, the conformal time. And then I will be discussing how the cosmological CPT theorem actually manifests itself at the boundary. And then from there, I will discuss, explain how actually CPT allows us to completely determine the phase of what's known as the coefficients of the wave function of the universe. And these coefficients or wave function coefficients are actually contain a lot of information, including the information required to compute what the actual observers are known as cosmological correlators. And I will then discuss how we can convert between wave function coefficients and cosmological correlators. And having then established that dictionary, I will then use our understanding of how to convert between wave function coefficients and cosmological correlators, as well as the phase formula, to derive a no-go theorem for cosmological parity violation. So the cosmological CPT theorem tells us that scale invariance and reflection reality, which is a discrete symmetry which any bulk unitary theory has to satisfy, implies CPT invariance. But we also derived a way to make converse statements of the original flat space CPT theorem and the cosmological CPT theorem in the paper that came out in September. And in these converse statements, that we were able to actually show how one can uh, derive the non-perturbative constraint of unitarity known as reflection reality by combining CPT and scale invariance. And similarly, one can define CPT invariance and reflection reality to get discrete scale invariance. Uh, the reason why reflection reality is such a powerful uh, powerful discrete symmetry is because it's a discrete symmetry which all bulk unitary spheres have to satisfy non-perturbatively. Hence, uh, this constraint uh, is a constraint which allows us to describe uh, bulk unitary time evolution in a non-perturbative way. This is a non-perturbative generalization of the cosmological optical theorem, which was derived fairly recently, a few years ago, and we thus have the non-perturbative statement that uh, it's a non-perturbative statement equivalent of reflection positivity, for example, in ADS-CFT. And this non-perturbative constraint uh, involves an analytic continuation in the spatial momenta and a complex Weyl transformation. And we can then actually express this constraint to orders of perturbation theory by identifying that the Weyl transformation actually leads to a dependence on the number of spatial dimensions and the loop number, as expressed here. And this, I should emphasize that this constraint actually holds at any finite eta as well as at the boundary at eta equals 0. But then what do the other two discrete symmetries of CPT and discrete scale invariants actually look like at the inflationary boundary? So to answer this, let us actually look at the scalar and spin S fields that we have in cosmology. And specifically, I'm going to be looking at bosonic or integer spin S fields, and I won't be discussing spinors in this talk. So what actually happens to scalar and spin S fields at the et equals 0 inflationary boundary? Well, to answer this question, we can just simply look at the equations of motion. So the equations of motion for scalar and spin S fields can simply be derived and shown to have this form. And one can ask, what actually what does this equation of motion actually look like at the limit eta equals 0? Well, it turns out that the Laplacian term in the equations of motion actually becomes subdominant, and this then tells us that the equation of motion becomes a simple differential equation which is solved by power law solutions. And because this is a second order differential equation, the power law solutions that we get, for example, for the scalar field, will involve two branches. Uh, so one which I've denoted as phi plus and phi minus here. And one of those branches will actually be dominant at the et equals 0 limit, specifically the phi minus branch highlighted here. And the scaling of this phi minus branch is dependent on what's known as the conformal dimension. And this conformal dimension for the case of scalar fields will run between 0 and d, where it will be d for a massless field, and it purely depends on the number of dimensions, the mass of the field, and the Hubble parameter. And for a generic spin S field, we find a similar relation where there is both a sigma plus and a sigma minus branch, and it is only the sigma minus branch which is dominant at the eta equals 0 limit. And similarly, we find that this sigma minus branch has a dependence on a conformal dimension, but this conformal dimension for the case of spin S fields also has a dependence on the spin of the field. And I should emphasize that we will not be discussing what's known as principal series fields, which are the fields which correspond to the point when delta, the conformal dimension, becomes complex. So uh, now that we've analyzed how dynamics actually manifests itself at the boundary in cosmology, we also need to now define an observable at the boundary. And here we're going to be working with the what's known as a boundary wave function, which has no dependence on eta. And similarly, the coefficients of this wave function, known as the boundary wave function coefficients, which I'm denoting by a bar on the top. And var phi here can denote any scalar or spin-s field. And as I said before, only the negative branch of the scalar and the minus branch of the scalar and spin-s field is the one that's dominant at the eta equals 0 boundary. And with this knowledge, we can then actually just use simple dimension analysis to actually derive the how the boundary wave function coefficients scale under a scaling of the spatial momenta by some scaling factor lambda. And it has this particular form, which depends on the number of external legs, the dimension, and the conformal dimension of the fields in the external legs. And then we can choose a particular discrete choice where lambda is equal to eta plus or minus I pi, and we get this form for discrete scale invariance at the boundary. And then using the fact that we know that reflection reality holds both at finite eta and at the boundary, we can use the group structure to construct a third discrete symmetry, which purely involves a relation between the wave function coefficient and its complex conjugate. And it turns out this is nothing but CPT. And one can actually arrive at this independently by purely looking at how CPT manifests at the boundary. And this is something that we did in the original Cosmological CPT Theorem paper. So CPT tells us that there is a relation between the wave function and its complex conjugate without any need for any analytic continuation of any of the parameters. So this then tells us that the phase of the wave function is actually completely fixed. And this is what we refer to as the phase formula. And remarkably, the phase formula will hold for any wave function coefficient, provided that it satisfies these 5 criteria. Firstly, that the space-time is de Sitter, but can also have scale-invariant boost-breaking interactions, for example, phi dot cubed with one scale factor in front. For the case of d equals 3, the Lagrangian is locally CPT invariant. The wave function coefficient is IR-finite, i.e. there's no log minus k eta terms, which we refer to as IR divergences, as this cannot be set to eta equals 0 because the log term blows up. And then this wave function coefficient involves fields only with real conformal dimension, i.e. there's no spinors or principal series, and that all fields satisfy the Bunch-Davies vacuum. And we can then see simply from this phase formula that for the case of a little d equals 3 as in our universe, we will have a purely real wave function coefficient if we have massless scalars or massless spin S fields where S is an even number, for example, the graviton. And similarly, we will have a real wave function coefficient if we have an even number of conformally coupled scalars or massless spin 1 field, such as a photon. However, if you have an odd number of conformally coupled scalars or an odd number of massless spin odd fields, such as a photon, you will actually get a purely imaginary wave function coefficient. And this is going to be important for the next part of this talk. So, to understand what the phase of the wave function coefficient tells us, let's actually look at how the wave function coefficients are related to the cosmological correlators. So to compute cosmological correlators, we can use the wave function to obtain a probability distribution function like in normal quantum mechanics, and then we can integrate over the fields that we want to compute. So for example, if I want to compute a trispectrum, I would need to do this integral with 4 bar phi fields, and then I would then compute the trispectrum. And then what this actually tells us is that the cosmological correlators Bn are proportional to this particular linear sum of wave function coefficients that I've called rho n, which is simply the wave function coefficients plus their complex conjugate with a flip in the spatial momenta. And it turns out we can actually just split rho n into a parity even and parity odd part. And this is going to be helpful for analyzing uh, uh, how to in order to derive a no-go theorem. And we can see simply when we do this helpful splitting that actually the parity odd correlator is purely related to the imaginary part of the wave function coefficient, since it's related to the difference of the wave function coefficient and its complex conjugate, which is the imaginary part. And the parity even part is related to the real part of the wave function coefficient, as it's related to the wave function coefficient, the sum of the wave function coefficient and its complex conjugate. So then we can infer that uh, if a wave function coefficient is purely real, this implies that the parity odd correlator must vanish. So through the phase formula and this understanding of how to convert between wave function coefficients and cosmological correlators, we arrive at the following no-go theorem for cosmological parity violation. Specifically, we know that in big D equals 3 plus 1 spacetime dimensions, parity odd correlators at the inflationary boundary cannot be generated at tree or loop level by models with only massless scalar fields and even spin fields such as a graviton, satisfying the Bunch-Davies vacuum. One can also have an even number of massless odd spin field or conformally coupled fields in the external legs as well, and you will similarly find that you can't get a parity odd correlator, and that's just because of what I explained before, that the wave function coefficients still stay real if you have an even number of conformally coupled and massless odd spin fields. And this also and provided that the Lagrangian is CPT invariant, locally CPT invariant, and that the theory computes IR-finite and UV-finite wave function coefficients, this no-go theorem will continue to hold. And if the last two criteria are met, it then tells us that if we do have massive spinning fields in our theory, then the parity odd correlator can only be sourced by what's known as the factorized contribution from the exchange of internal massive spinning fields. So it can't come from what's known as the connected diagrams. And at loop level, it tells us that we are generically going to have the possibility of a parity odd correlator, because at loop level, uh, we we cure what's known as UV divergences by going to non-integer dimensions, and this is a process known as dimensional regularization. And when we go to non-integer dimensions, as we saw from the phase formula, we are generically going to get a complex phase. And this is actually something that has been shown explicitly in certain calculations. And what I will show in the paper after the no-go theorem paper is that this is actually a generic feature of loop diagrams, that you get a generically complex phase and therefore can have a parity odd correlator. Thank you for listening, and if you have any questions, feel free to either find me at Parity Violation from Home next week or email me at my email address here. I'm looking forward to discussing with you all next week.